So now we're going to talk about a technique called infrared spectroscopy. So back to the electromagnetic spectrum, we're now looking at this region of the electromagnetic spectrum, infrared. So it turns out that light that has energy in the infrared range tends to correspond quite nicely to differences in molecular vibrations in a molecule. So it's still spectroscopy, so it's still the same general principle that we're going to be shining some form of light or energy onto a molecule. It's going to absorb that energy and be promoted into an excited state, and we're going to be monitoring which wavelengths of light are absorbed. So it's the same principle as when we were doing UV vis. So with UV vis, we were looking at electrons being promoted from one orbital into a higher energy orbital, and that's a big energy gap that corresponds to light of energy in the UV vis range. It's the same principle with IR, but now we're going to be changing the vibrational mode of a molecule, and it turns out that that's a smaller energy gap that corresponds to light of IR energy. So this is what an infrared spectrum looks like. On the x-axis we've got wave number, so that's inverse wavelength, and on the y-axis we've got transmittance. So this is kind of upside down because you imagine that if the molecule is absorbing light at a particular wave number, then the transmittance is low. And so this is actually peak. So everything that's pointing down is actually a peak where the molecule is absorbing light. So this particular molecule, this is the IR spectrum of this particular molecule. And as you can see, there's a whole bunch of different signals all the way along here at slightly different wave numbers. And that's because there are many different types of bonds and functional groups within this molecule, which all give distinctive signals here. So it's quite a complicated picture, but let me talk you through how you interpret it. Basically, I already told you that energy corresponding to IR radiation causes vibrations, and there's several different kinds of molecular vibrations are possible. So for example, you can have symmetric stretching or asymmetric stretching, you can have scissoring, rocking, twisting, wagging. Lots of different kinds of cute little molecular motions that can occur that have different energies. And it turns out that different bonds have distinctive IR absorbances. It's affected by things like the strength of the bond. So stronger bonds have fast vibrations. It's affected by the masses of the two atoms. So if one of the atoms is very light, it'll cause a faster vibration. Stretching and bending are slightly different from one another. Even hybridization can affect things. So you don't need to remember these numbers. The point is that features of the bond will affect the wave number of light absorbed. So we're coming back to, this is a skeleton of what an IR, kind of like a blank IR spectrum here, and these color-coded regions shows where your eye should naturally be drawn when you're looking at an IR spectrum. This brown part over here, that's the fingerprint region where there's lots of carbon-carbon bond vibrations are in here, so that doesn't really actually give you very much interpretable information. It's usually very complex. So usually ignore that region of the IR spectrum. This green region here, around about 1600 wave numbers, is important because that corresponds to vibrations associated with CC double bonds. So if your molecule contains a CC double bond, you'll get an absorbance here. This pink part is another very important part of the spectrum, around about 1700 wave numbers. If your molecule contains a CO double bond, it'll absorb somewhere in here. The yellow region here is, you'll get a signal if your molecule has a triple bond, and then way out here, around about 3200 to 3600, you will see signals corresponding to OH or NH groups. So let's see some real examples. Here's the IR spectrum of this molecule here, and there's two important things to point out. The first one here is a signal corresponding to CH stretching. Many molecules, of course, will have a signal out here. This signal is probably more distinctive, around about 1700. That corresponds to the CO double bond in the molecule. Here's another example. This is butanoic acid. So there's two important signals here. The first one is this very huge broad signal here, which is the OH stretching, and then the other one is another example of a CO stretching, once again around 1700. So that corresponds to the C double bond O here and the OH. Finally, a bit more of a subtle example. Now we've got three amides. These three amides here, and they have differences, but this one is a tertiary amide. This one's a secondary amide. It's got one hydrogen on the nitrogen. This is a primary amide. It's got two hydrogens on the nitrogen. And you can see In each case, all of these molecules contain a signal in the CO region, so that doesn't really distinguish between them very well. But what's interesting to note is the NH region. So this molecule doesn't contain any NH groups, so it's blank in this part of the spectrum. This molecule contains one NH group, and there's a stretch associated with that NH. This molecule contains two different NH groups, and lo and behold, we've got two different signals here. So this is a useful region of the spectrum for looking at the differences between these molecules. So there you go, that's a little summary of how to interpret IR spectra.